Okay, so we're going to start our exploration of graphing things. Before we get down, though, to X and Y and all that, let's just kind of talk about what a graph does, what a graph looks like, what a graph is. There's no vocab for this section. Something I want to bring to your attention, though, is this idea of two variables. Okay, so notice here, volume versus height. Down here, time versus volume. Now, generally speaking, when time is involved, we usually make that the x-axis. Okay, just kind of one of those side notes. It's kind of important. But when time's involved, because it kind of makes sense to go left to right linear with time. So anyway, let's take a look here at the first the example up here before we actually get to the problem. So the graphs below relate the height of the water to the volume of water in each container. Which graph goes with which container? Justify your reasoning. So you've got to take a look here. Notice how this one, volume, right? As volume increases, height increases, and then all of a sudden, it seems like the height kind of changes. It's no longer just linear. So the height of the water changes, but the volume continues to increase. I would say that's probably this one, because it's pretty even. All of a sudden, well, now the height's going to get slower as the volume increases because it gets wider up here. Now we're taking a look at this one. Notice that the volume increases quicker than does the height. That's why it's a more shallow graph. That's probably the short, fat one. And here, the volume increases less quickly than does the height. That's probably this one. So the height's going to go quicker in here as the volume increases. So that's what we're looking at. There's actually a couple of quiz questions that are just, again, kind of understanding what a graph is telling us as opposed to the X and the Y and all that stuff, which we will get to, I promise you. This one's kind of a fun little problem to think about. The graph shows the volume of air in a balloon as you blow it up until it pops. What are the variables? Describe how the variables are related at various points on the graph. So notice here, time continues, right? Again, we said times quite often, or should mostly be the x-axis, because it's the input. It's certainly not an output. Time is, it's there no matter what. The volume is the input. Now this one's kind of fun. Notice here, as time increases, you're blowing in air and the volume increases. All of a sudden, time continues and the volume stops increasing. That's because you stopped, you pinched the balloon, took a breath. You didn't add any more air. You took a breath into your lungs so you could continue to add more air as you blow. And then again, you pause. You take a breath so the volume is not increasing, but time is still going. Do the same thing again. And one more time, again, taking that breath right there. Blow, 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 until it pops, and all of a sudden the volume is zero immediately. Okay? That's what that one shows us. Okay, so you got it here. What are the variables in each graph? Describe how the variables are related at various points in the graph. So this one's kind of a fun one. Board length and time. Again, notice time is at x-axis. Let's go over here, minutes, right? Time is at x-axis. Length of the board. So notice here, the time continues, but the length of the board doesn't change. So boom, the board is shorter, right? Just like immediate. Going along here, and nothing changes. Boom, the board is shorter. Going along, boom, the board is shorter, right? So what's probably happening here is you're setting up your saw, right, moving the board into place, and cut, the board is shorter. And again, you're taking time to move the board into place so you can cut it, and you cut the board shorter. And taking time to line up that board, and the board gets shorter. And then you're done. So, don't want to cut any more off. You might, cut off a finger or something. So anyway, here again, time and length are certainly the variables. The length of the board remains constant for a time before another piece is cut off. So that's what we're looking at there. Taking a look at B. June's cell phone costs. So costs here on the y-axis, that's the output. Input is minutes of call. So notice you're going along here and your cost doesn't go up, but you're using minutes. All of a sudden, the cost in minutes starts going up. So our variables are time and cost. And notice the cost remains constant for a certain number of minutes. After that, you must have run out of minutes, so you start having to pay more, right? I got minutes, and then I run out, so it starts going up because you ran out of minutes. Alrighty, matching a table and a graph. Now we've talked about, or you're going to talk about soon enough further, discrete graphs and that sort of thing. I kind of forgot because I forgot to shoot this video before I shot the other one, so luckily I realized at the last second. But anyway, we'll talk about that later, the discrete graph thing. It says a band allows fans to download its new video from its website. The table shows the total number of downloads after 1, 2, 3, and 4 days. Which graph could represent the data shown in the table? Okay, so notice here, Again, we don't have numbers, but time is along that x-axis. Total downloads here. Sort of a constant rate. Each day it kind of goes up. Here it sort of seems to peak off, slows down a little bit, right? This one, it starts out slow but picks up pace quickly. And here, as time goes on, less and less downloads. So, the relationship, again represented by a table, we're looking at time versus total downloads. Those are two variables. So in the table, the total number of downloads increases each day, and each increase is noticeably greater than the previous increase. So again, notice here, first day's downloads, second day's, and it picks up quickly, right? So each day, they download even more at a noticeable rate. That's probably this one right here. Because again, notice, first day, second day, by the time you get that fourth day, there's a lot of downloads. It picks up fairly quickly. It is definitely not linear. Alrighty, so your second got it. The table shows the amount of sunscreen left in a can based on the number of times the sunscreen has been used. Which graph could represent the data shown in the table? So again, notice, number of uses, 0. There's 5 ounces left. 1 use, 4.8. 2 uses, 4.6. 3 uses, 4.4. Notice here it's going down at a constant rate, right? 0.2 of an ounce each time. It's a constant rate. So you're going to look for a graph that's pretty much constant. Now, this one, it runs out, right? Number of uses, it runs out to 0. We didn't see that here. That's not a 0 at the end. This one, it looks like there's like people using it quickly, then they kind of slow down on using it. That's not what this shows. This is a constant use. So this one, a straight line, again, is a nice constant use. So we're looking at graph C for that one. Okay, now I'll tell you at the outset, you will have a quiz question like this. I think these are kind of fun. Now, on my quiz, you're going to draw a line and label the different parts. The thing that kids miss most often is forgetting to label the individual parts to telling me what's happening. All right, so it says a model rocket rises quickly and then slows to a stop, and as its fuel burns out, it begins to fall quickly until the parachute opens, after which it falls slowly back to Earth. Sketch of a graph that would do this for us. So again, notice here 0, so time on that x-axis again, height on the y, again the input is time, and you shoot that rocket off, right? And as the fuel burns, so here it rises pretty quickly still, but as the fuel burns out, it stops rising, and then it starts falling back towards Earth, and then it would have continued accelerating that, right? But the parachute opens, and so it slowly falls back to Earth after that. So notice again the labels that go with each of that. Let me say that again. Again, it's on the ground, 0 height, light it, accelerates quickly, or I should say rises quickly. And it runs out of fuel, so it starts slowing down, stops rising. It's probably about right here that it runs out of fuel, I bet. And then it stops rising. And then it starts falling pretty quickly after a few moments. And again, it would have fallen more quickly and crashed into the Earth, but the parachute opened. So it opens, so it goes slowly back to Earth. Alrighty, suppose you start to swing yourself on a playground swing. You move back and forth and swing higher in the air, then slowly swing to a stop. Sketch a graph that represents how your height from the ground might change over time. Label each section. We'll take care of B here in a second. Let's do that real quick. I'm going to show you what I have here. Obviously, I didn't draw it. I kind of cheated. But again, time is going to be that x-axis. I don't know how much I can stress that. Time is x. Y is the distance from the ground. So you start out, right? You're obviously not straight on the ground because your seat has to have a little bit of clearance, like, leg room. So you jump on your swing. So you're a little bit off the ground. And you swing a little bit and go up. And then you swing back towards the earth, right? Because think about how swing goes, back and forth, back and forth. So you would increase your height a little more each time as you pump your legs, right? Faster and faster and faster. So again, you rise higher, then you come back towards the earth. Notice each time you come back to this same height there, right? That same height each time with your leg room from the ground. Then you pump a little harder and get higher and higher. Then you swing back towards the earth, and you reach that point again. Then pump higher and higher and higher. Then you stop pumping and let it kind of just oscillate back and forth until you come back to a stop. Okay? That's what we're looking for here. Part B, if you jump from the swing instead of slowly swinging to a stop, besides a broken leg, how would the graph in part A be different, and explain? So the end of the graph would show a would decrease sharply. So let's say you got to the height of it, right? It would just go. It wouldn't go straight down because you still have that time piece where you're moving forward because you're not immediately on the ground, right? But it would be kind of like a line going boom into the ground. And this time it would actually maybe hit the ground instead of going back to this, like, the leg room space. So boom, hit the ground, right? So that's what you're looking for there. And you will have test questions like quiz and test questions like this.